Hello, welcome to video 42 in the lecture Advanced Mathematic Modeling. In this video now I want to show you some property of power law distributions, which is one of the reasons why these distributions are so fascinating. So we have a distribution like this, so what's so special about this? And the thing, what is special about this kind of distributions is that they are scale free. And so in the next videos we will more and more look at the scaling of certain properties and so what's happening if we just blow up a system from very small to very large, we increase the scale. How are properties of a system changing when we change the scale? And power law distributions are special in the sense that they are scale free. Let's look what we mean by this. And to start this discussion, let us compare again our two favorite distributions, the exponential and the power law. So let's say we have here again the exponential distribution, where we say the probability of our random variable goes like parameter c to minus x, or we can write it as e to minus another parameter x. Yeah, so an exponential distribution. And we want to contrast this to a power law distribution. Where our distribution is not c to minus x, but x to minus alpha. And so the question is, so what's now the fundamental difference in the distribution if we have either c to exponent x or x to exponent alpha? So let's have a look at our exponential distribution, and we have done this. So we have seen, okay, it's a decaying distribution, p of x, and in the power law distribution we have also decaying distribution, only here with a cutoff value. So at first glance they look quite similar, but now we have seen if we take a certain value here, a certain value x, and now we can go a certain distance, a shift x plus b, and when we have an exponential distribution we know what the value here is at a horizontal shift, because the probability at x plus b, now we can plug this in here, so this is e to minus a times b times e to minus a times x. So we can write this as a function of b times our probability p of x. And so this means if we go a certain distance to the side, yeah, our distribution is just reduced by a factor which depends on this b. So this value here is just a function of b times p of x. So that's the reduction. So this reduction, when we go a certain distance to the side, is just a factor which depends on the distance that we go to the side. Now, how is this when we have a power law distribution? Or, okay, this was this x naught. Let's take here the value x. And now we want to have something similar. And in the power law distribution, we cannot go to x plus something. We have to go to value b times x. and see what is the value, the probability of b times x. And then if we plug this in, the probability of b times x, and we put this in here, so we see this is a function of b times the probability of x. So we get a similar reduction. So we get here a reduction, and this reduction is just a function of our parameter times p of x. But in this case here, it's a scaling parameter. This x has to be multiplied by something, and in the exponential, the x has to, we have to add something to x. So power law distributions have this fundamental property. I mean, this property here, I mean, that's known in elementary math as the half time of an exponential function. Yeah, so the halving time, doubling time. But this here is a property of scaling. So what do we mean by scaling? Scaling, we mean if we have our distribution, yeah, and now we see what's happening if we scale everything. Every value is multiplied by a number. We blow things up. If we blow things up, so we scale things here, and then so see the probability of the scaled variable is the old probability just by a constant. So you could say, I mean, the power law, these distributions mean higher values we have lower probability. So if we go to the right, the probability to achieve a number is reduced. But this reduction, in this case, is the same on all scales. So let's now continue only with the power laws. So let's say a power law. The reduction of p with increasing x so the reduction, the way the curve here is getting smaller and smaller when we go to the right, when we increase x, this reduction is the same on all scales. For a power law distribution. And let's see what this means. Let's take an example, because that's really a fundamental property. Let's take an example, for example, city sizes. And I told you that city sizes are approximately power law distributed with an exponent about 2. Alpha is about 2. And so now let's say, what does it mean that city sizes are scale have this property, and this property, we mean this is called scale-free property. And the scale-free property means that this reduction is the same on all scales. So let's say, we could say a city, for example, if we have our data, and the data is city of 10,000 people has a frequency of fourth frequency as city of 10,000 people. So let's say if we go here from one value to the next, from 10,000 to 20,000, if by this we reduce now the city size, the number of people city size by a factor of 4, yeah, then the same thing would happen if we scale the whole thing. This means if we have this power law distribution, that a city of now 20 million people has fourth of the frequency as a city of 10 million people. So now this means like this decay here that we have is the same on all scales. It doesn't matter if you're speaking about 10,000 or 10 million or 10,000, it doesn't matter. Always the reduction is the same if we scale everything. Yeah? And this means if you look at certain some cities, and you find, for example, that you have 4 times more cities. Let's say that you would have a picture from a satellite on your country, and you would see, okay, you have 4 small cities on average, and then 1 larger which has a larger size. So you would see something like this. You would see 4 times small cities compared to a city with a double size. From this you could not figure out if the size of one city is now in the order of thousands or in the order of millions, because this kind of patterns you would find on all different scales. And now I showed you this argument in this way, that we say if we have a power law distribution, we obtain this property, yeah? And so power law distributions are scale free. And now we could argue in the other way around. If we have a scale free property, what kind of distributions have this? Are this only power laws, or are there other probability distributions which have the scale free properties? So we could, and I want to make a small calculations to show you that only power law distributions have the scale free properties. So now let's we assume we have a scale free property. So assume we have a probability distribution which has this property g of b times p of x with some function g which we don't know. And now we want to know what kind of distribution is this. So first we can take x equal 1. And this should also of course hold for the value x equal 1. And then we know p of b equals g of b times p of 1. Or in another way, g, so we can calculate this function g of b equals our distribution at value b divided our distribution at value 1. Okay. And now we can plug this in here. So we have our distribution at the scaled variable equals p of b divided by p of 1 times p of x. Yeah? And so what we did in the moment, we just calculated this function g of b here. And now this here should hold for all values of b. So this is a function of b. For all scaling parameters, we call this b a scaling parameter. Should hold for all scaling parameters. And we will call this a scaling parameter b. And so this is a function of b, and so we can take the derivative by b. So let's take the derivative, and yeah, so we have here the derivative of the function b at the position bx, and we take the derivative to b here, and then if we take the inner derivative, this x stays at the side. And then we have here the derivative of our function b, p prime of b. This p of 1 is just a factor, which is not modified by the derivative. And we have this p of x, which is also a factor, which is not changed. Yeah, so that's just a derivative of this. And now we use this derivative at the positions at b equal 1. Okay, so we put here b equal 1. Then we have x times, if b of is 1, then we just have the dp over dx, yeah, because this b is not there, we just have the derivative of our function p, but now the derivative to the variable x. Here we have again the derivative at the position 1 divided by p of 1 times p of x. Yeah? And so now by this kind of magic we now have obtained a differential equation for our probability distribution p of x. Yeah? And so we can solve this. We have to divide by x, and then we have dp over p dp over p equals p prime from 1 over p1 times dx over x. And now we can integrate on both sides. Then we have logarithm of p of x, if we integrate this, equals p now I have to be careful that I didn't make a mistake here. Yeah, it's correct. So p prime of 1 divided by p of 1. Now here we have logarithm of x, and then plus an integration constant c. And now how do we get the integration constant? If we set x equal 1, then we see x equal 1, then this whole cancels because logarithm of 1 is 0, and then we see that the constant c is just the logarithm of p of 1. And then we can now put this constant in here. We take exponential on all sides, and then we see that p of x equals p of 1 times x to minus alpha, and this exponent alpha is just given as minus p prime of x, the derivative at the position x, divided by p of 1. And so indeed we see that, we see that if we start with this assumption, we have a scale-free distribution, we can make a simple calculation and see the only distribution consistent with the scale-free property is a power law distribution. maybe at this point I should it's a good point to give you a note in the literature. So there is a very good review about power law distributions, and this is a paper by Mark Newman. Power laws. Pareto distributions. And Zipf's law. So this book appeared in Contemporary Physics. This paper. Contemporary Physics in volume 46. Pages 323 to 300, and this appeared in 2005. So that's a really excellent review about power law. So I think I will put this review in the StudIP so that you can, if you want, can have a look at this. So a lot of this stuff that I was showing here in the lecture about power law distributions you find in this this excellent review by Newman. But what I just found, and that's why I mentioned this at this position here, Newman, he had a small mistake. So when he calculated this, he got this ratio here wrong. So which is also a small hint that you should not believe everything that you find in the literature. You always have to calculate for yourself. There's a lot of typos in the literature, but the whole the story anyhow was correct in Newman. So like if we start with this kind of assumption, the scale-free property, we can see that the power laws are the only distributions which fulfill this. And that's one of the reasons why it's so of particular interest if real data is really following power law or only approximately, because we want to know, is the distribution scale-free. That's for the moment, and in the next video we will look at some other interesting properties of power law distributions. But for now, thank you.